The last section of this chapter covers something really cool, which is the Doppler effect. And I'm going to start by going through the concept behind the Doppler effect, since it can be a little tricky to understand, and then we'll look at the equations for two separate scenarios. We have to think about sound separately from light in this case. So starting just with the concept, what is the Doppler effect? It's going to occur when the source, a source of a wave, and an observer of the wave are moving relative to each other. Now, this also has to do with the medium, so this would be much more complicated if both people are traveling on a car and the car is traveling with respect to the air, but we're not going to make it that complicated right now. So in general, what we care about is the motion with respect to what the wave is traveling through if it's sound, and you can usually assume that either your observer or your source are stationary with respect to the air and that the other one is moving. Now, in the case of light, this is actually relativistic, not meaning just relative, but like Albert Einstein equals mc squared sort of stuff. We are not going to derive where it comes from, but you're going to be handed what the equation is. So what's a little bit confusing is that there's actually two different Doppler effects. They come from two physical origins. They have a similar impact, but we use one with sound and one with light. So let's now try to understand what is actually happening. And right now we're focused really on the case of sound. So let's start thinking about our source moving. Now the book doesn't do the derivation for the observer moving, and it's really easiest to think about this being the source moving. So we have four dots, counting's hard, which represents where the source is at different moments in time. Notice that we are saying that this is, well, initially t equals 0, but then at the period, right? So if we basically say that it starts by emitting a crest, right? A crest, we're going to have another crest when it gets to 1 period, another crest when it gets to 2 periods, another crest when it gets to 3. And the reason I'm pointing out that it's a crest is, again, remember that if we want to talk about circular or spherical waves, which is what we have to do now, the Doppler effect is something that doesn't really make sense for one-dimensional waves. We're going to have those circles, and each circle represents a crest. So we have our wave that is, giving a sound, and so we have a sinusoidal form, and each dot here is separated in time by a period, and our source is moving. So at later times it is further to the right. Now we have two people in order to think about what they're going to actually detect. So this has some frequency. Our source is emitting at some specific frequency, but we can then ask, what frequency does Nancy detect and what frequency does Pablo detect? Notice that in Pablo's case, the source is moving away, and that in Nancy's case, the source is moving towards. So that's actually going to give us a difference. We don't actually get the same effect for both Pablo and Nancy. So hopefully this picture makes sense before we move on and actually add the wave fronts, because that makes it much more complicated. So what we have to think about here is that we're at some specific moment in time. Where we are in this picture is t equals 3 period. So what that means is our source is currently right there. So at t equals 0, that was 3 periods ago, and our source was here. So when the source was here, we had a crest, but it's actually had 3 periods to expand. And so based on the relationship between wave speed, and notice that in this case wave speed and source speed are two different things, that it has been able to expand out 3 wavelengths. So the red circle is centered on where the wave was, where the source was at that moment in time. At the later moment in time, the 1t moment, our source was here, and that wave again expanded out spherically, and it's had 2 periods to expand, so it's made it 2 wavelengths. So you're still getting circles, and each circle is centered on where the source was when the crest was created. Because again, keep in mind that each wave front, each circle corresponds to a crest. But since our source is moving, the circles are not centered with respect to one another. What you then can notice is that at Nancy's side, you actually have a wavelength that is much closer together. On Pablo's side, you have a wavelength that is much more spread apart. And then when they convert this into a frequency, everyone here agrees as to what the wave speed is, because if this is sound, everyone agrees if this is room temperature that it's 343 meters per second. So once you have your wavelength and you know what your wave speed is, you get what your frequency is. So again, this can be a little tricky to think through, and I really encourage you to do so. That we said that it's giving off crests spaced at one period. This is the source speed, which is different than the wave speed. And so each crest in a circular 3 or 2-dimensional sort of way is centered on where the source was at that moment, but the source was moving. So Nancy's going to have shorter wavelengths, Pablo's going to have longer wavelengths, which means that they get 2 different frequencies. So, please pause, look at these slides, look at the picture in the book, and make sure that you understand what's happening here. And again, keep in mind that this is the model for a moving source where your source is something like sound. This is not quite the model to use for light.